restart in order to remain within the schedule. In this session, we're going to have four nice presentations around the area of planning of sustainable microgrids. And we have presentations from University of Leeds, from Indonesia and RDI, and from Uganda, from CRIC. I will introduce the speakers one by one before they present. So the first speaker is from the University of Leeds, is Dr. Dehghan, Shahab. So Shahab is a research fellow in smart energy systems at the University of Leeds, and before joining Leeds, he was an associate professor at the Faculty of Electrical Engineering at Qazvin branch of Assad University in Iran. He received a first-class MSc and a PhD with distinction in electrical engineering from the University of Science and Technology. And he's a recipient of various awards, honors, and grants, including the EPSRC Impact Acceleration Award in the UK. Has published more than 45 peer-reviewed papers in high-impact journals and conferences, including the flagship transactions journals of the IEEE PES community. He has been involved in fundraising and implementing several projects with over £125,000 of funding as principal investigator or co-investigator or research co-investigator in the UK and Iran. So Shahab is going to talk to us about project towards resilience and sustainability in Alderney energy system using a Python-based energy planning tool. So Shahab, the floor is yours. You have 15 minutes.
Okay, can you hear me?
Yes, I can.
Okay, thank you. Hello, everyone. I'm Shahab Dehghan from the University of Leeds, and today I'm going to present our microgrid planning project on Alderney Island. This project was funded by EPSRC Impact Acceleration Award and Alderney Electricity Limited to accelerate the impact of the Crescent High-Risk project. Also, it is a collaboration between the University of Leeds and the Cyprus University of Technology. In the rest of my talk, at first I will present an overview of this project. Then I will summarize the main features of PyEplan, which is an open source Python-based energy planning tool developed at the University of Leeds for creating sustainable microgrids in remote areas. Afterwards, I will focus on the mathematical formulation of the investment planning module in the first version of PyEplan. Then I will present the main results of our case studies on Alderney microgrid. And finally, I will summarize the main conclusions of this project. Now, let's move to the first part of my talk, which is an overview of the project. Alderney Island, with a population of 2,000 people, is the third largest of the Channel Islands between the UK and France. This island, with an area of 3 square miles, as shown in the right-hand side map, runs a closed, centralized energy system that entirely relies on imported fuel oils for electricity, heating, and transportation. The only energy supplier on the island is Alderney Electricity Limited, or AEL, which provides for both electric and heating loads. Electric power on Alderney Island is centrally generated by 8 450 kVA diesel generators and supplied by a network of underground cables. So the resilience of the energy supply on Alderney Island is not high because AEL only relies on imported fuel oils. So with this background, the main objectives of this project are firstly, extending the developed planning tools at the University of Leeds to investigate potential solutions for resilience and sustainable energy systems with low carbon emissions in real life. Secondly, suggesting optimal reinforcement solutions to the Alderney microgrid and evaluating their impacts on increasing resilience and sustainability. And finally, identifying the main barriers to bridge between theoretical and practical planning tools for real-world applications. So we have utilized in this project PyEplan, which is an open source Python-based energy planning tool developed at the University of Leeds to create microgrids in the Crescent HiRes project. PyEplan is coded using Pyomo, and its first version has been released on PyP. In general, PyEplan collects different inputs such as estimated load demand, estimated renewable power production, and network topology. It also includes 3 different modules. The first module is focused on data processing, and it provides needed inputs for the second and the third modules. The second module provides the optimal investment plan for microgrids, while the third module provides the optimal operation plan for microgrids under different techno-economic constraints. PyEplan has also specific advantages as compared to other commercial software packages for designing microgrids. For instance, PyEplan is useful for both static and dynamic security analysis, uncertainty management, and joint investment and operation planning, which are impossible on other software packages such as Homer. Okay. Now let's move to the mathematical formulation of the problem, of the investment planning problem. The objective function of the investment planning problem minimizes the total investment and operational costs under all financial and technical constraints, including power flow equations and adequacy, security, and resilience constraints. In general, the investment planning problem is a highly nonlinear and non-convex optimization problem under different types of uncertainties. The nonlinear and non-convex characteristic of investment planning model result in a complicated optimization problem which cannot be solved by commercial optimization tools straightforwardly. For instance, the nonlinear and non-convex solution space of a simple 3-bus test system is illustrated on the top figure. Clearly, the solution space of a practical microgrid will be more complicated than this 3-bus illustrative example. Also, uncertainties may result in a considerable financial loss or serious issues related to adequacy, security, and resilience of the microgrid. For instance, the load profile of a simple household during only 4 successive years as a high-frequency uncertainty source is illustrated on the bottom figure, and its variations can be detected clearly. To resolve these limitations, a linear formulation is used in the first version of PyEplan. Accordingly, a 2-stage stochastic optimization is utilized as a non-deterministic optimization method wherein investment variables are here and now decisions and they are not a function of uncertain parameters. And operation variables are wait-and-see decisions and a function of uncertain parameters. Also, the K-means clustering technique is used to characterize the interday and intraday uncertainties of load demands and renewable power productions. To this end, Inter-day uncertainties are characterized by representative days belonging to different clusters, and intraday uncertainties are characterized by risk-seeker, risk-neutral, and risk-averse representative days corresponding to 5% quantile, 50% quantile, and 95% quantile of each cluster. In addition, power flow equations are approximated by the Lin-Dist flow equations, and quadratic line flow equations are approximated by a polygon approximation. So the final optimization problem will be a tractable mixed integer linear programming problem, which can be solved easily by commercial software packages. Okay, now let's turn to case studies. In this figure, the one-line diagram of the Alderney microgrid is illustrated. It includes 450 kVA diesel units and 22 transformers. Also, the yearly patterns of load demands and renewable power productions in 2013 are shown in this slide. According to these figures, the peak load on Alderney microgrid is about 1.2 megawatts, and the capacity factor of solar and wind units are about 16% and 54% respectively. So the capacity factor of the wind unit is significantly higher than the solar units. In this research, to obtain the optimal reinforcement plan for the Alderney Island, 6 different case studies are considered here, including different number of wind units, solar units, and battery units. In addition, case 6 considers all investment candidates in addition to the current diesel units in the Alderney microgrid. In the first study, only one best nominal and worst representative day are considered. According to the results of our studies, the optimal investment plan, which is indicated in green, belongs to case 6 under the best nominal and worst representative days. Under the best scenario, only one wind unit is selected. Also, under the nominal scenario, only one wind unit is again selected, while one of the current diesel units on Alderney Island is in operation at several hours. And finally, under the worst case scenario, cases 1 and 2 are infeasible, surprisingly, as indicated in red in table 1, and none of the renewable units are selected in case 6. The main reason is that under the worst case scenario, there is no wind or solar power within a single day. So it can be concluded that considering only one representative day, even by using the K-means clustering technique, may result in inaccurate or even infeasible solutions. To resolve this issue, in the second study, all investment candidates are considered simultaneously, and the number of best, nominal, and worst scenarios are increased from 1 to 100 scenarios. All best, nominal, and worst representative days, in this case, obtain identical results and identical investment plans under 100 scenarios. However, this optimal solution is even obtained by considering only 5 nominal representative days as indicated in table 2. So considering a sufficient number of representative days is really important in planning studies. Therefore, in summary, it can be concluded that first, free open source tools with solid mathematical formulations can be used for creating real-life microgrids. Secondly, the optimal design, even in small-scale microgrids, cannot be obtained without the proficient planning tool estimating the potential of renewable energy resources. Third, the lack of sufficient data is one of the main challenges in proper analysis and optimal design of microgrids, particularly in rural areas. And finally, inaccuracy in network modeling and mathematical formulation may be translated into a considerable financial loss. Thank you for your attention.
Thank you very much, Shahab. I would like to point that the chat function is open. So if you have any questions to ask to any of the presenters during their presentation, you can put it in the chat. At the moment, there isn't any questions. Maybe I will start off. One of the questions I had was that this project was in collaboration with industry. So can you tell us a little bit, because we do a lot of academic projects and everything goes very nicely. We have all the data, we make a lot of assumptions. In this one, you really had to work with historical data. Can you tell us what were the challenges that you found?
The main challenge for creating microgrids in rural areas and even some areas in developed countries is related to lack of sufficient historical data. For instance, if you are going to design a microgrid in a specific village, we don't have any historical data. And when we don't have any historical data, we may design a microgrid which is not optimal in practice. So there are examples, for instance, in Uganda, on Kalangala Island, they have a microgrid, but it's it's not optimal in practice because the installed capacity of this microgrid is higher than the required, is significantly higher than the needed load demand on the island, and the main issue is related to willingness to pay for electricity. And also in our recent project on Alderney Island, we had a similar issue because we had historical data for load demand, but we didn't have any historical data for renewable energy resources, and we just used satellite data for wind power, for instance. So it is the main issue related to historical data, but there are other issues related to mathematical modeling and considering security of the microgrid. So the main challenge is in rural area is related to lack of historical data.
Okay, thank you very much. There are a couple of questions. One is from Elizabeth. She's asking, how much time does it take for the software to plan a microgrid for a certain rural area, providing that the data is complete, that we have access to data? I mean, it's about, I guess the question is more about the execution time.
It depends the number of consumers, the number of candidates that you will consider, because the problem is MP hard. What does it mean? It means you cannot predict its computation time before solving the optimization problem. But for our case study on Alderney Island, the CPU time was less than 1 hour for all case studies. That is, I think, a low computation time for a planning problem. And also we will consider representative days that they will incorporate intertemporal constraints, so it will affect the computation time. But again, I think its computation time is not high, because we have used a linear approximation for power flow equations. So I think it has a reasonable computation time as a long-term planning software package.
Okay. And I think there is one other question from Hossein. Says, I think likes for some comments on the optimization algorithms, and what is your view on meta-heuristic algorithms versus mathematical optimization algorithms, I guess, for this specific example.
For this specific example, we have utilized a mixed integer linear programming problem, and this is solved by rigorous optimization techniques such as branch and bound algorithm. So you can use meta-heuristic algorithms or rigorous mathematical optimization techniques, but in this project, we have used mathematical optimization techniques with rigorous backgrounds, and yes, and it is possible to change your solver. For instance, you can use Cplex, you can use I don't know, Gorobi, Mosaic, or every solver that you prefer.
Okay, I think there is a follow-up question by Sven, saying, as you mentioned about n-hardness, did you apply any simplifications to your input data, to your overall input data? And NP-hard, yeah.
Excuse me, can you repeat the question, please?
I will read as you mentioned NP-hardness, did you apply any simplifications to your overall input data? And which simplifications? And then did you implement your own mixed integer problem algorithm, or did you use some commercial solvers?
We have used commercial solvers because they are really proficient for solving large scale mixed integer linear programming problems. And also, I think for every study, we have some assumptions and some simplifications. For instance, it is not possible to, if you are going to design the microgrid, for instance, 10 years later, it is not possible to consider and predict all future realizations of uncertain parameters such as load demand accurately. So you need to consider some approximations. In this study, we have used K-means clustering technique to consider some representative days instead of consider all days of a specific year or several years of the planning horizon. So it is the main reason that we have used the K-means clustering technique.
Can you mention which specific solver you used for this study?
I have used Cplex with an academic license, but it is not for free Cplex. But there are other open source solvers for mixed integer linear programming problems.
Okay. There are a couple of more questions, but we'll have to keep this for offline because we're already 10 minutes past. I will forward your questions to Shahab, and I'm sure he will get back to you. So let's move to the next